Right above us, it's out there. I know, it's weird. It's kind of how my hair is. That's awesome.
Here we go. We're going to start doing some problems now. And we're going to start actually in our book on page 708. So if you get your book out, you'll notice on page 708 that all of the problems are word problems. And that will be the case. These are all word problems. What kind of word problems? Well, let's just look at number one. How many ways can we line up 3 people for a photograph? Now, with only 3 people, it would be easy to draw a picture of all the scenarios and then just count them up. But if there were 13 people, that would take a very long time. So let's strategize this for a minute. You are going to line up 3 people for a photograph. So if we drew a picture of that, we'd have 3 blanks. We're going to line up 3 people. We're going to put a person here, put a person here, and put a person here. Okay? So I'm going to line up my front row here. Maggie, Delaney, and John. All right, so I'm going to grab one of them, and I'm going to put them in this slot. How many choices do I have? 3. So I have 3 choices for that first blank. That does not mean I'm putting 3 people in that blank. It means I have 3 choices. Okay, so I grab one, put them in the slot. Now, I need to grab another one. How many choices do I have now? Just 2. And then I got to fill the last slot, and there's only one person to choose from, right? So the number of ways that I can arrange 3 people in a line is what we call 3 factorial. Have you seen that symbol before?
Yes.
The exclamation point, the fact that's a factorial. The factorial symbol means whatever the number is, you start with that and then multiply by every single number down the line. So 3 times 2 times 1. If you had 8 factorial, it would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now the good news is there is a factorial button on your calculator. So if you have your calculator, get it out. And if you don't have a calculator, you're going to want to pay attention because you are definitely going to need a calculator to do all of these calculations. Okay, so let's suppose we're going to arrange 8 people in a row. So if we were going to arrange 8 people in a row, not 3 like we did up here, we're going to arrange 8 people in a row, would you agree that that would be 8 blanks and 8, 7, 6, 5, 4, 3, 2, 1? But I don't want to write all that out, so I'm just going to say 8 factorial. So I type 8, and then I find my math button, and it should be in the first column. Find it, math. Click all the way over. You have a menu of items across the top. Click all the way across to probability, P-R-O-B. And as soon as you get over there, if you look down the list, do you see the factorial symbol? So click down, enter. You might have to hit enter again, and you get 8 factorial, which is, I don't know, 40,000 and something. Okay? Now, 2 things we just learned. We learned how to get a factorial on our calculator, and that's going to be extremely handy. Please remember how to do that. So let's go through it one more time. We type in whatever number we have. So 12 factorial, we type in 12. Then we go to our math menu, click across to the probability, and then choose the exclamation point. Okay? The other thing, hopefully, we're getting from this is, if we want to arrange, whether it's people or books or anything, if we want to arrange things in a row, if there are 10 things, they can be arranged in a row how many ways? 10 factorial. If there were 15 things, they could be arranged in a row 15 factorial ways. So the general rule is n things can be arranged in a row how many ways? N factorial. Okay? Big important idea. N things in a row, n factorial. Okay? Now, we got a couple of variations to make to that, but I want to do a couple more problems first. Number 5. We're going to have a king-queen pair, and there are 4 queen candidates and 3 king candidates. Anybody have an idea how many pairs there would be?
12.
12 is exactly right. Kids, it's the same idea. I'm not really arranging them, but I'm going to pick a queen. I get to pick 1 queen, and how many choices do I have? 4. And I'm going to pick a king, and how many choices do I have? 3. So altogether, how many choices do I have? 12. Now, I want to show this to you one time, because that really needs to make sense to you. So let me draw a picture of it. Let's say the girls, the queen candidates, are A, B, C, and D. If I pick A, I can pair her with king 1, 2, or 3. Would you agree with me with that? So there are 3 pairs if I pick queen A. Well, what if I pick queen B? Don't I have the same 3 options? So there's 3 here, there's 3 here. How many are there going to be here? 3. And how many are there going to be here? 3. So how many are there altogether? 12. 4 times 3. Here's another example. I have 8 jumpers, 10 shirts. You know I don't care if anything matches. Wear anything with anything. How many outfits are possible? 80. 8 jumpers. Each one of the jumpers can be paired with 10 shirts. That's 80 outfits. Right? Okay, called the fundamental counting principle. Number 6, same thing. Different problem totally, but exactly the same concept. 3 roads will get me from A to B. 4 roads will get me from B to C. How many different ways can I get from A to C through B? Exactly. I got to get from A to B. How many choices do I have getting from A to B? How many choices do I have getting from B to C? Actually, this is 3. And this is 4. So there are 12 altogether. Now, it's going to get a little more complicated than this, but it's important you get the basic idea here. How many choices do you have for the first step? How many choices do you have for the second step? Multiply them together. One more. Number 8. How many letters are you going to pick? 3. So you're going to pick 3 letters. How many choices do you have for the first one? No, you don't have 3 choices for the first one. You have 22 choices for the first one. How many letters are in our alphabet? 26. What did they do? They excluded how many of them? 4. So that leaves you with 22 letters to choose from. So you have 22 choices for that first blank. If you had all your letters in a pile here and you're going to reach in and pick one, there'd be 22 in that pile. Okay, so you pick one and you put it in that first blank. Now, did you notice? No repeated letters. So how many choices would you have for the second blank? 21 and then 20. What are you going to do with these 3 numbers? Multiply them together, and that will be the answer. What if you were allowed to repeat? What would change in the setup of the problem if you were allowed to repeat? It'd be 22, 22, 22, exactly. Okay? Now, let's do a couple of variations here. Let's take the word fox. How many ways can I arrange the letters? In the word fox. What do you think? Bingo, 3 factorial. How many letters are there? 3, we're arranging them in a row, right? How many ways can you arrange 3 letters? 3 factorial, perfect. What about the word rain? 4 factorial. On test day, I will expect you to give me numerical answers. I don't want to waste time in class typing these in, but the actual answer here would be 6. 4 factorial is 24. The calculator will tell you that, or you can just multiply 4 times 3 times 2 times 1. What about the word C? Now things are a little bit different here. We have to be careful. What's different about this word? It's got some repeated letters, doesn't it? And when we are arranging things, we have to be on the lookout for repetitions. All right, so here's what I'd like to do. I'd like to take a look at this word. And I'm going to go ahead and do the letters in different colors. There are 3 of them, so I should be able to arrange these 6 different ways. So I'm going to go ahead and write down the 6 different ways using my different colors. That would be a different arrangement, right? Because the letters are switched. Okay. This is harder than it looks. I got all 6 of them there, the 6 different arrangements. But if I didn't do it in color, what would happen? If I didn't do it in color, these 2 would be the same arrangement, wouldn't they? And these 2 would be the same arrangement, and these 2 would be the same arrangement. To handle repetitions of anything, however many items you're arranging, start with that. So we start with 3 factorial, just like some of you said. There are 3 letters, that's 3 factorial. But then you must divide by the factorial of the repeats. So in this particular word, there are 2 E's, so I will divide by 2 factorial because there are 2 E's. These are all the letters, and these are the repeated letters. That should work out to be 3. There are 3 different arrangements. Okay, let's do the classic example, Mississippi. How many ways can we arrange the letters of the word Mississippi? Okay, how do we start? What do we do first? Count them up. How many are there? So we start with 11 factorial. That's quite a large number. We start with 11 factorial. Now I've drawn that division symbol in there because what have I noticed about my word? There are repeats. Okay? So each letter is handled separately. So there are 4 I's. So I'm going to divide by 4 factorial. Those are the I's. There are 4 S's, so I'm going to divide by another 4 factorial. There are 2 P's, so I'm going to divide by a 2 factorial. And then I type it in on my calculator. Please be careful. Anytime, we've talked about this before, anytime there's more than one thing in the denominator, what do you have to be sure to do? parentheses. Please don't forget those, or you won't get the right answer. So let me see if we can type in the right answer. I got 34,650. Anybody want to confirm that or dispute it? Logan?
Wait, so you can't make the denominator 10?
Oh, no. No. Remember, 4 factorial means 4 times 3 times 2 times 1. And another 4 factorial would be 4 times 3 times 2 times 1. And then a 2 factorial would be 2 times 1. There's no 10 in there. Would you agree with me?
Yeah.
Yeah, no, those can't be combined. There's nothing, no. Good question, no. Okay? All right, let's see, next. Got a couple more ideas here to talk about. So we've learned now, what's the latest thing we've learned? How do we handle repetitions? We divide by however many there are, factorial. And that's any identical items. Okay. Next, I'd like you to consider this question. In how many ways can I arrange 3 people in a row? You better be able to answer that question.
6.
In how many ways can I arrange 3 people in a circle? Now, we've talked about the row. In fact, we generalized it. N things in a row is n factorial. So if you are going to see 3 people in a row, the answer is 3 factorial, 6. Does that change when you put them in a circle? Well, I don't know. Let's draw a picture of it and see. If we had 3 people in a row,
Wasn't expecting a circle.
that would be ABC, ACB, BAC, BCA, and CAB, CBA. There are the 3 people in a row. Now I'm going to take each of those and make them in a circle. It's going to look more like a triangle, but it's like a circle, okay? So my circle, I'm going to have A, B, C. And here I would have, here are my 6 patterns. So then I'll have A, C, B, B, A, C, C, B. Oops, I skipped one. Which one did I skip? BCA, thank you. All right, so there they are arranged in a circle. Do you notice anything about those?
Just rotated.
Oh, some of them are just rotated. For example, if you look at this one right here, look at this guy, and then come down here and look at this guy, and then come over here and look at this guy, what do you notice about those 3 tables of people? Aren't they really in the same order? The people are in the same order, but the table has just been rotated? These are not different arrangements. These are the same. What about this one, and this one, and this one? Are they also the same? Yes. In fact, 3 people in a circle is not 3 factorial, it's 2 factorial. Each pattern occurs 3 times. So it's 3 factorial divided by 3, which is 3 times 2 times 1 over 3. Do you see how I got 2 factorial out of that? So what if I had 4 people?
3 factorial.
3 factorial. In a circle, you can arrange one less factorial ways. So if you had 12 kids, and I was going to line them up out there on the bench in the hallway, how many ways could I line up 12 kids on the bench in the hallway? 12 factorial. But if I invite them to a bonfire at my house, how many ways can I arrange those 12 kids around a bonfire? 11 factorial.
A lot of ways.
Got it? Some of you look really tired, really bored, and I know, I think this is exciting stuff. You might not, but here's the deal. We've learned some really important concepts, and you're going to be hanging on to them. How many ways can n things be arranged in a row? N factorial. How many ways can n things be arranged in a circle? N minus 1 factorial. Right? How do you handle arrangements of repeated items? Divide by repeats factorial. Right? Big ideas. We got some more. Big ideas. I'm going to put 2 questions up here on the board. I want you to tell me if they're the same question or if they're different. And if you think they're different, you need to tell me why. Both cases, I have 10 kids in my group. So I've got this group of 10 kids. In how many ways can I choose a president, vice president, secretary? Oh, let's throw a treasurer in there too. And then the second question is, and you're just going to determine, because same 10 kids, you're just going to determine if these are the same question. In how many ways can I choose a leadership committee of 4? So you see what's going on. I've got my 10 kids here, my club. This is my club. And in one case, I'm asking you how many ways I can pick a president, vice president, secretary, treasurer, 4 kids. And in the other case, I'm saying I need a leadership committee of 4. So both cases involve 10 kids picking 4 of them. So same question?
No.
Why not?
Because in the second one, you just like make 4 people group, and then the first one you got to order them.
You have to order them. That is the key component. In this question, order matters. If you are going to pick a president, okay, let's say these are the 4 people I'm going to choose right here. These guys, they're my chosen 4. If I pick Carter first, then he's the president. And then Zach maybe is vice president, and so on. Order matters. If I'm going to pick a leadership committee, does the order matter? The way I pick them? You just want to get picked, right? It doesn't matter what order you get picked. So for the first question, order matters. For the second one, order doesn't. When order matters, you have what's called a permutation. So number 1 is a permutation problem. Have you heard that word before? The word permutation implies arrangements, and arrangements means order. When you arrange things, you're putting them in order. Your calculator will answer this for you real easily. The notation we would use in this problem is either 10p4 or p10.4. Both notations are used. Your calculator uses this notation, but you'll see both of these. Let's understand, this means there are 10 total things, in this case people, and I'm going to pick 4 of them. The P stands for permutations and is my clue that order matters. So there are 10 people, I'm picking 4 in order. Maybe you saw the P button because it's in the same place your factorial button is. So I want you to press 10. and go where you got your factorial. Do you remember where that is in the math menu? Math, click across to probability. Do you see your P button there? So you press 10, then you press your P button, then you press 4, and press equals. And what does it say?
5,000.
5,040. Tom Stripe.
On my calculator it says NPR. Is that?
Yep, that's it. That's it. This is, Tom, this is NPR.
Oh, okay.
N is the total number of items, R is how many you're choosing. Now, in this problem, order doesn't matter. This is called a combination problem. When order doesn't matter, you just want a combination of 4 people. All jumbled up, you don't care what order. The notation for that is either 10C4 or C10-4. Did you see your C button? I forget if it's above or below your P button, but it's right there with it. What's that answer? 210. The biggest issue most of us have when we're doing combinatorics like this is deciding whether order matters or not. Don't overthink it, use your common sense. If order matters, you're going to do P. If order doesn't matter, you're going to do C. Let me give you another example. Okay, in how many ways, I'm going to have about 18 kids in my group this time. In how many ways can I give 3 different students a pencil? And in how many ways can I give 3 different students a pen, an eraser, and a calculator? So just to be clear, in both cases, I have 18 kids and I have 3 prizes. In this case, I got 3 pencils. I'm going to give away 3 pencils. Here I got 3 different prizes. I got a pen, eraser, and a calculator. Both problems involve 18 kids choosing 3. Are they the same? Are they both P's? Are they both C's? Is one a P and one a C? What's the story here? First one's a C. Because if I have 3 of the same prizes, do you care if you are picked for second or third? No, you're going to get the same prize. It doesn't matter, right? So number 1 is a combinations problem. So this would be 18C3. But what's different about this one? The prizes are different, so the order you get picked matters to you. If I'm giving away a pen, eraser, calculator, don't you want to be picked third? Yeah. So this is a key problem. Got it? Now, in the good old days, there weren't calculators. And sometimes even now, in the current good days here, we have to be able to evaluate combinations and permutations without the calculator. So we are going to talk about how we might do 7C3 and 7P3 without a calculator. And the reason this is important is there will be problems where you have to do XC4 divided by x minus 1 c7 or something like that. And you'll need to reduce that fraction. You cannot type that in on your calculator, so you're going to have to be able to understand how it's done by hand. So it's real simple, really, really simple. If we are doing, we'll start with this one. If we're doing 7p3, that's 7 factorial divided by 4 factorial. Now, I don't think anybody probably has a question about where I got the 7, right? Where'd that 4 come from, do you suppose? 7 minus 3. That's exactly right. You subtract these numbers, and that's what goes in the denominator. So if we had 8p5, or 8p5, that would be what? 8 factorial over 3 factorial. One more, if we had 12p2, that would be 12 factorial divided by 10 factorial. Now, keep in mind, if you actually had to like work this out, what does 12 factorial mean? 12 times 11 times 10, 9, dot, dot, dot. And 10 factorial means 10, 9, and so dot, dot, dot. Well, what's going to happen? All that's going to cancel, so the answer to this would just be 12 times 11. So these can all be simplified that way if you need to. Katie Swanton, I used to have this magnificent sign hanging by my clock. It said, "Time will pass, will you?" But then I had to take it down because it was destroying the kids' self-esteem or something, I don't know what. But anyway, the bell will ring when it rings. We still have a few things to learn. Okay, so that's how we handle that. So everybody got the P's down? All right, what do the C's look like? Well, they start actually the same way. That's exactly the same. But they have an additional divisor, 3 factorial. So when you're doing a combination, and these are the ones we do most commonly, actually. We do more combinations than anything else. When we start doing probability, all of our card problems will be combinations. So we have 7 factorial divided by 4 factorial, I subtract, and then 3 factorial, that number right there. So if I had 10c6, that would be 10 factorial divided by what? 4 factorial, 6 factorial. If I had 20c17, that would be 20 factorial divided by 3 factorial, 17 factorial. Very, very good. Okay? Now, I know we're going to do a couple card problems here in a second. Not probability yet. But I want to show you something. Walter's cleaning out his stuff, and he had some old math books that he gave me. And you guys, you really have no appreciation of what it was like to take this class back when he and I took it. We had to buy, because we're calculators, we had to buy this book. I have one at home too. It was called the, we call it our CRC tables, but it's the standard mathematical tables. Everything your calculator does is in this book. So if I wanted the square root of 17, I would look it up in my book. If I wanted the cosine of 58 degrees 12 minutes, I would look it up in my book. Everything you can possibly imagine is in this book. We carried this with us always. This was like our Bible. So we could find everything. So, I mean, you guys, we want tangent 18 equals x over 12. Remember, like, how high is the school in the tree problems? And you just type that in, bingo, and you got it. Well, we could look up the tangent of 18 degrees or whatever in our book, but then guess what we got to do? We got to do that arithmetic by hand. because we didn't have a choice. There's no other way to do it. So
That sounds
I
fun.
want you to understand, we took the same class you're taking. We learned the same math you're learning, but we couldn't type 12 NPR2 on our calculator. We had to do everything by hand with this book right here. If you ever want to look at it, you can. It's just, I mean, it's absolutely amazing. But this was our Bible. We carried that with us everywhere we went. Okay, so now we're going to do one more problem, and then I'm going to let you pause because Katie's bored. So here is the question. How many, okay, are you all familiar with a standard deck? Because you got to be, because we're going to be doing all kinds of card problems. A standard deck of cards has how many cards?
52.
52. They're divided up into 4 suits: diamonds, spades, clubs, and hearts, right? If you don't understand what I'm saying, you need to get your hands on a deck of cards and study it. Each suit has 13 cards in, and 3 of them have faces on them. Kings, queens, and jacks, they're called face cards. And then there are 10, 9, 8, all the way down. An ace it's not a 1 really, it's called an ace, okay? So here's the question. How many 5-card hands, we're talking about a standard deck now, how many 5-card hands contain exactly 2 queens?
I don't like that.
Good morning. Good morning. Please excuse this interruption. At this time, we are going to go down as if we were in a tornado drill. It was a severe thunderstorm warning until like 8:45. Some heavy lightning is outside the school, so we're going to take that precaution.
I love the screaming of them.
Whoa. Please stay right here. Our learning will continue. We are saying,
No, I like this.
I do need to go out and help shuffle kids around. So while I am doing that, I want you talking about this problem and figuring it out.
But there's a tornado. Every single time the announcements come on. What?
Steel spoon.
They're not playing around.
Oh yeah, I saw that.
There's no tornado.
Right?
Definitely a tornado.
Wait, what is it really?
Bro, the suit of the tornado. Let me down.
There's a girl. It was a man with black shorts on and a green shirt. And Kayla goes, "That's not a girl." She's like, "It's a poor girl." Kayla's like, "No, it's not," and just like, "Bye."
Dude, there's no room back here. You're not even on the class. You're not even
Are they cold? Yeah. Are you gonna warm it up? Or are you just going cold today?
Those look great.
You jump out a window when you do it?
He's been sitting there like, ooh, that looks good. Ooh, that smells good. Hopefully. I'm going.
Dude, every single time he goes on the announcements now. But just a tornado drill.
Baby!
Yeah, I can. I just see
You can't hear it, it's okay. For some reason you only hear my voice.
John, did you sign up for new student orientation?
I think it's because it's behind it.
24 and 25. I did it soon so you don't like work by yourself. You, me, and Lindsay and Anna. Maybe you don't want to go.
LOL.
What about Charlie? It's because I think it's because Joey's going.
No, it's he wanted to go, but then she talked to Sally and my brother, and they were like, seriously.
Friends have broken our trust for.
Shut up.
What about Charlie?
Hey guys, at least we're getting Adam back.
No, green cap. Left and right is green capsule. We're using your interaction. But I mean, there could be
They said it was really heavy.
Wait, so this is actually like
Raincoat, right?
an actual real thing? Why the fuck? Hell yeah. Yeah. Hell yeah, we're fine. People are just running outside.
We're drinking our coffee.
Are we?
I'm so proud of myself for it.
No, there's no room here. Oh, is it county today? Do we actually have county?
No.
Yeah. No. Stop being your dad.
Ben, what do you have after this?
Get out!
Harvey Harris.
Leave! You live in Penn State.
It's probability. You don't have to.
That's why you don't see.
Maria.
was like, where's the lacrosse
Beginning
game?
chapter.
Start
Venn diagram.
So I'm like pulling out a bunch of kids and I was like, bye guys. And they were like,
You're a terrible.
I was like, okay, you're obnoxious together.
Mr. Cole was at our practice yesterday.
I know. Was she like?
There's no way it's not. Kayla's dad was at our practice yesterday. We were just like, what are you doing?
She saw him walking like away, and like I was literally just watching her. She was like flipping away, like you know, as he's walking up the I just got there.
My charger's downstairs.
No one did this problem. She's gonna be so disappointed in us. You should probably turn off this video.
Yeah. Yeah, they do. Like, totally.